We're going to talk here the next couple of times about the so-called conic sections. There's four of them. It's the parabola, which we're familiar with. We're most familiar with opening up or down parabola, shifted or whatever, but we've done those. But we're going to add on to that the sideways parabola. And so we're going to look at ones that open right or left also. Probably the most familiar with these is the circle, and we'll talk about what the equations of that looks like. Now an ellipse, it's kind of the egg shape. I guess not, an egg is not quite as symmetrical as an ellipse, but yeah, it's kind of a flattened out circle, you might say. Or now there is a elongated, there's also two types of ellipses. Let me just put it that way. You can have one that's longer this way, and you can have ellipses that are longer up and down. We'll talk about all that. And then the hyperbola, probably the most complex of these four conic sections, but a hyperbola, kind of like a parabola, except there's two of them, or one of the differences. There's two branches, we call it. This is the right and left branches, hyperbola, or you can also have an upper and lower branched hyperbola. Like I said, it's really a lot different than the parabola, but much kind of looks like it, except there's two of them. But we'll talk about these. And these are, just let me mention real quick, my little prop here, since they have it in the room. The reason those are called conic sections is because they're just different ways you slice a cone. If you slice a cone just straight through, 90 degrees or whatever you want to call it, yeah, the cross section is a circle. If you do it at an angle, or one certain angle, instead of 90, well, if you cut it that way, you got an ellipse shape. And then if you cut it other ways, you get the parabola. Now, to get the hyperbola, you kind of need a double cone. Imagine there's another cone with the tip touching this one. That's how you get the hyperbola, because if you slice that double cone, you get two branches with the cross section. So anyway, that's the four conic sections. Now, let's talk about the equations. What equations generate these is really the goal, the question we're asking ourselves here. Well, we already know the parabola, one of them anyway. We know the up or down parabola. That's y equals x squared, or shifted, however, vertex shifted and all that. But so our regular parabolas are, we'll focus on the ones that aren't shifted right now, and then we'll talk a little more about shifting next time. But so this is without shifting. Let's call it y equals ax squared. Now, like I said, that was not shifted at all. So we've got a vertex. We'll talk about, most of these we'll talk about two things. We'll talk about vertices and foci, or focus points. Foci is just plural of focus. But anyway, we talked about the vertex a little bit. And since this one's not shifted, where's the vertex of this one?
0, 0.
0, 0, yeah. We'll shift some things around, but for today, our vertex, we'll start with 0, 0. Now the A, of course, that tells me opens up or down, right? This is a little bit of review. It tells me whether it opens up or down, but it also gives me what is known as the vertex. And so let me go through the handout first and talk about talk about it, and then we'll get into more details about that parabola here in just a second. But let's look at that handout I gave you before I forget. On the handout, I just have several examples. Got to go through real quick here, not spend a whole lot of time. We'll do a lot more with graphing these, because the way I did it on the handout is I just did points on that, and some of them it took quite a few points, and that's not the way we want to do it. Be as efficient as we can. But I started here with one, and that's this is one that is shifted. Y equals x squared minus 1. That's a parabola that's shifted down 1, right? That's just the x squared parabola shifted down 1. And so we've got that vertex there at 0 and -1. We'll talk about I got kind of hid myself over there, but we'll talk about a focus point also. Let me just mention that here real quick. The focus point, there's different ways you can use the focus point, but one thing about the focus point, and it turns out in this case, I believe it would be somewhere along in this vicinity. But one way you can apply the focus is that if you think about sound waves or light rays, or the ones that come in to my kind of in the same plane, if those light rays come down straight down like this, think about the horizontal one, those light rays are going to bounce off, and this is a reflective type material, let's say. Those light rays are going to come down, and they're all going to, no matter where they hit, those light rays are going to come here and focus at this point. That's the focus point, one of the applications of the focus point. So any of these that come kind of parallel to the axis of symmetry, those are all going to come into that focus point, okay? So that's one application, why we might want to find that point also, but we'll talk about how we find that later on. So that's our parabola that opens up or down. You know, if we made it a minus, it would minus x squared. It would be opening down parabola. But kind of go through these pretty quick here. All right, so number 2, we've got x equals 1/4 y squared. All right, and then I did a table, like I said on the handout. I'm not going to write the whole thing up here because it's on the handout there. But basically, yeah, I've got 2.25x, y is plus or minus 3. Just, you know, picking random, if you will, sort of random, x values, and then finding the y values for that. And of course, certain x values, if x is -1, we can't get a x value of -1 because we're sparing the y there. So there's no solution, real solution on negative values. But anyway, all told here, if I then graph these points out, point by point, 2.5, 3, 2.5, -3, and all that, here's what I get. It's a parabola, but what's different about it? It's sideways, right? Or I call it sideways. There's different terms you can use, but it's a sideways parabola. So that's what's different about the graph. Now, what changed here as far as the equation goes? What's different?
X and Y are switched.
You got y, x squared here. Here you've got x, y squared, right? So one of them squared, and depending on which one's squared, that decides whether it's up or down parabola, right? Up or down or sideways. You with me there? Okay? So take note of that. We'll talk more about it here in a second. All right, number 3 is our, what shape we've got there. It's x squared plus y squared equals 25. And again, I did this the hard way because we haven't talked about it at all, but if you do all those points, I got -5 down to +5. Well, and 0. Anyway, what happens there is you get, for a lot of the x values, you get 2 y values, all right? And so that's why you get this shape, I guess, one reason. But here's what you get, notice. Here's 5, here's -5, here's +5, here's -5. What shape am I getting there? It's a circle. Now, what's different about this equation?
All squared.
Both squared, yeah. So I've got x squared and y squared, and then I've got another number, as opposed to one of them squared, one of them not squared, right? So that's, of course, a key ingredient to having a circle. Both of them are squared. Now, the thing about that is, though, saying it that way, I've got x squared over 25 for number 4, plus y squared over 16 equals 1, okay? So both of those have x squared and y squared. But when we do the table here, kind of starts off, again, on most of the x values I picked out, I'm going to get 2 y values. And so again, that's why you're getting, you know, here I've got -4, +3, and -3. So I've got those, that's what I'm saying. I've got 2 y values for each x value. That's defined anyway. Same thing happens on this, but what shape does that give me? It's an ellipse. So if I plot all these points out, point by point, yeah, I get an ellipse. So this one gives me a circle. Number 3 gives me a circle. But number 4 gives me an ellipse. So there's a little more to it than just saying, well, both of them are squared, so I get a circle, right? Because both of them are squared, you could get an ellipse. And we'll talk about kind of that difference there. One thing, all right, so one thing that's different about this, notice this one equals 25, this one equals 1. And so the equals 1, that's going to be kind of key to setting up an ellipse. And we'll talk about more in detail that in just a second. But if I divided here by 25, that would make that 1. And those divided by 25, that would be x squared over 25, y squared over 25 equals 1. Instead of having 2 different numbers there, those 2 numbers are the same for a circle. So it's related, but a little bit of difference. All right, and then the last 2, like I said, the complicated one. Oh, before I leave ellipse here, let me just mention, on an ellipse, we talked about, on this one I talked about the focus on the parabola there. On an ellipse, there's 2 focus points, foci, and they're located, for an ellipse, they're located on that longer axis. You know, I've got this axis from, what is it, -5 to +5? Yes. And this one's +4 to -4. So that longer axis there, that's where the foci are located on an ellipse, and there's 2 of them. One on either side of the center, which in this case is 0, 0. So those are the foci. And let me go ahead and mention, just to kind of introduce these, there also are 2 vertices on, which is plural of vertex. There's also 2 vertices for ellipses. This is vertex, call it 1 right here, and this is vertex 2 here. And the vertices are the endpoints of that longer axis. Because like I said, on some of these ellipses, they can be longer than they are wide, you know what I'm saying? And so the vertices are going to be the endpoints of the longer axis. So anyway, just FYI. We'll talk more about that in a second.
What about the foci? Is there one on the circle?
On a circle, yeah, it doesn't, because because of the way it works, there's technically the center is the focus on those, but we don't really find the both sides for the circles. Number 5. All right, so number 5, we've got x squared and we've got y squared, but it's x squared over, 25 minus y squared over 16 equals 1. And if I do the table of values, I'm not going to write all those out here. Just mention that, again, for every x value, if you choose the x values, you get a couple of y values. You do the same thing for the y value. But notice in the middle there, I don't get any values kind of in the middle of this, because those don't give me real values for the y values. And then there's some other, just to put a couple of random points there, but in the middle here, there's not any real values for the y values. And so what that means is you got to break your gap in your graph. This is what you have, which we called, what was that called? Hyperbole, yeah. Now, since I have number 4 still up and number 5 here, what was the difference here, you think? Why did this one give you hyperbola? This one gave me an ellipse.
You're subtracting this.
Yeah, there's a subtraction in between. If it's set up like this, equals 1, x squared, y squared on the same side. If you got a minus between the two, that's a hyperbola. Whereas if you have a plus between the two, that's generally going to give you an ellipse. All right, so that's pretty easy, right? Not too bad. What I mentioned also on this one is the foci, or the vertices first. Call them vertex 1 and vertex 2. You got 2 vertices on an ellipse. I mean hyperbola as well as you do as an ellipse. And you also have 2 foci, and here's where the foci usually lie in hyperbola. They're out here. Focus 1 and focus 2. And it's where those are going to lie. Instead of, the way I look at it is, well, different ways you can look at it, but the vertices are inside the foci here, and it's just flipped on the ellipse, you see. I guess that's kind of one way you could look at it. The foci are inside the vertices here. On hyperbola, the foci are outside the vertices. Does that sort of make sense? Anyway, we'll talk about that more coming. One other thing too, I know I'm covering a lot of ground here, but we'll do it in more detail in just a second. One thing else different, this looks like a parabola, but it's not, because there's 2 of them, 2 branches. The other thing that's different, a parabola doesn't have asymptotes, right? It's slanted out one way or the other, but on a hyperbola there are some asymptotes. And kind of what you do is you draw this, what's called the fundamental rectangle, and I'll tell you how we do that in just a second. But you draw this fundamental rectangle, and the asymptotes are the diagonal of that rectangle. So you've got an asymptote through the diagonal here, and then you've got a second asymptote through the diagonal there. And that's going to kind of be the key to drawing this. Instead of doing this big long table, that takes a lot of time, and we don't want to do it that way. This gives us better information, and it's a little easier. So, all right. Now, what I mentioned on number 6 to finish up this handout is one really big thing here. If I do the table out, x and y values, you got the table there. Here's what I get. If I graph all those points, I get a hyperbola because I've got the minus between them. But what's the difference?
The X and Y are separate.
I've got the x and y are switched, but it's a upper and lower branch, right? This one we say has right, right, left branches. Because there's a branch on the right, branch on the left. This one has a branch upper and a lower branch. And so what's the key there? Yeah, it's a minus between the x squared and y squared, but what's the difference again? What'd you say was the difference? How come this one's upper and lower, you think, as opposed to this one right and left? The x squared's first here, so if the x squared's first, it's right and left branch. The y squared's first, it's upper and lower branch. Okay, and the reason, the very simple reason, because if you think about it here, if I plug in x to be 0, I'm going to get some y, if plugging in x is 0 gives me y-intercepts, just to refresh our memory on that. Plugging in x to be 0 gives me the y-intercept. That's going to give me y squared over 16 equals 1, which is, that's going to be plus or minus 4. That's why you get the 4 and the negative 4 here, more or less. It has y-intercepts, but what if I do the reverse and plug in x to be 0 to find the y-intercepts? Well, that gives me that equation. Is that solvable? That's negative x squared, multiply both sides by 25. Negative x squared equals 25, divide by negative 1, x squared equals negative 25?
No.
That's not solvable, right? Or it's not real numbers. So there's no x-intercepts on this thing, you see. There is y-intercepts, but there's not x-intercepts. And just the reverse is true here, right? There's no y-intercepts. So you don't get anything crossing the line. So just an easy, little quick way of why. Why is it like that? Besides the table tells you. Anyway, all right. Is that good? Any questions on that?